Welcome to the second video in the first concept of this course, where we are discussing the diffusion of benzene from a PVC pipe into a water supply. In this video, we'll be looking at the applications of this model in MATLAB. In this module, we will revisit the necessary equations for the model of the concept, model the concept itself in MATLAB and view the results of it, and introduce the quiz for this module. Please enjoy. The first of the necessary equations for this model is the ordinary differential equation of a concentration of a solid substance diffusing into water over time. As you can see here, dc dt times v is equal to k times a times the quantity of c sat minus ct, where c is the concentration of the substance, v is the total volume, k is the reaction constant for the reaction, A is the surface area of the solid substance itself, C sat is the saturation concentration of the solid substance in water, and Ct is the concentration of the substance at a given time. There are two more necessary equations for this model, the first of which is above. A is equal to pi times d times L. In this case, A is the surface area, d is the diameter of the pipe, and L is the length of the pipe segment we are using. Please note that the pipe has been assumed to have open ends, and therefore there are no additional surface area components at each end of the pipe. Additionally, V is equal to pi times the quantity of d over 2 squared times L, where again V is the volume, d is the diameter, and L is the length of the pipe segment. In order to solve the differential equation we have established for our system, we will be utilizing the MATLAB built-in function Ode45. But what exactly is Ode45 and what does it do? According to the MATLAB documentation, Ode45 is a versatile ODE solver and is the first solver you should try for most problems. In our case, we will be utilizing the listed MATLAB syntax for Ode45 to solve for the independent and dependent variables in our system to then later plot these numbers. According to the syntax, a set of two variables, t, y, which is your time and your dependent variable, is equal to Ode45 with the following inputs: ODE fun, which is your ODE function, to be defined later in a function definition, your t-span or your time span, which is the total length of time you will be running your ODE for, and your y0, which is the initial value of your function. In our case, we will employ these with some slightly different variable names to produce values for the time span as well as the concentration of benzene in the water over time so that we can then plot the equation. Now on to the MATLAB code for this model based on the equations we have previously established. In this first segment of code, we do the following things. We begin by clearing both the command window and the workspace. We then begin to establish our constants. Here we say that B0 is equal to 0. This establishes the initial concentration of the benzene in the water as 0 grams per liter. We then establish the necessary time components for the model. T underscore total is equal to 1,000, represents the total amount of time the model will run in seconds. T step is the time step for the model. Here we have set T step equal to 1, saying that the time step for each component of the equation will be 1 second. Finally, T span is equal to a vector that is set from 0 to T total stepped by T step. This creates the total quantity of time we will need, along with the appropriate steps of time, to run the model effectively. The next segment of code is the Ode45 solution as well as the plotting functions. Here we can see that we have set the time t and concentration conc equal to the output of the Ode45 function, where we call the function ode to be defined later across the time t span with the initial concentration b0. Both t-span and b0 were defined previously in the code. With the outputs of t and conc, we can then go into plotting the data. Here, we use a basic plotting function where t is the independent variable and conc is the dependent variable. We then label the title of the plot as well as give the plot itself x and y labels with time in seconds and the concentration in grams per liter. As mentioned in the previous slide, we must define our function in order to use it in the Ode45 solution. Here, we define our function as dB dt, B standing for benzene, equivalent to ODE, where the independent variable is t and the dependent variable is b. We then define our constants necessary for the equation. Kb is the reaction constant for benzene. In this case, it is 5.64 times 10 to the negative 3. We then have the surface area of the pipe, where the pipe diameter is 3 inches and the pipe length is 100 feet. This gives us our surface area of 729.66 square decimeters. This is converted from the original square feet. In addition, the volume has been calculated, again converted from cubic feet to liters, to be equal to 139.01 liters. Then we have our saturation concentration for benzene, Bsat, equivalent to 2.17 grams per liter. We then write the definition of our function, dB dt, is equal to, then using the equation we established earlier for the concentration of a solid diffusing into water, as Kb times A, all divided by V, multiplied by the quantity of B sat minus B. Note that we must then end the function in the next line, or else the function will not call properly. As mentioned in the definition of ODE45, we will require a function definition to be plugged into the ODFun slot. For our case, we will set dB dt, where B is representing the benzene and T is representing the time, equal to ODE, which will take the place of ODEFun, as a function of T, time, and B, benzene concentration. In the definition itself, we must first begin with the necessary constants. First, we have Kb, which is equal to 5.64 times 10 to the negative third. Kb, in our case, represents the reaction rate constant. We then move on to A, which is representing the surface area on the inside of the pipe, and that is equivalent to 729.66 square decimeters. Please note that this was converted from originally feet squared. We then have our volume, V, equal to 139.01 liters. This was converted from cubic feet. And our saturation concentration for benzene, Bsat, which is equal to 2.17 grams per liter. As previously stated, our differential equation, dB dt, will then be equal to the quantity of Kb times A divided by V, multiplied by the quantity of Bsat minus B. Please note that with any function definition, you must have it both at the end of your code itself, as well as capped off by typing in the word end. This will seal the function and let MATLAB know that anything contained within the limits of function and end are intended to be part of the function. As you can see here, we now have a fully assembled code in a very specific order. Here, we first begin by clearing both the workspace and the command window to avoid having the overlap of any variables from any previous codes. We then define our constants for use throughout the code. Mostly here we're referring to the time. Then we write the call for the ODE45 function where we reference the ODE function defined at the bottom and we do our plotting information after that. The key thing to note here is the section break where function dB dt is at the very bottom of the code. Defining our ODEs with a function definition is required to be at the bottom, as would any other function definitions we would want to define for this code for future use. Sure, we can write the code for the model, as well as establish any equations we might need. But what does the model look like visually? What are the outputs of the code we have written? What you see on the screen before you is the plotting results of the plotting codes as established in our model previously. As you can see, the labeled plot for the concentration of benzene in water due to the PVC pipe degradation follows a very quick logarithmic growth that plateaus at its saturation value of 2.17 grams per liter. This is represented by the blue line on the plot. After completing this module, please do the following quiz. Using the sample code below, i.e. see the quiz documentation for the code or reference the code we have established in this video, and the scenario and assumption discussed in the previous videos, determine the impacts of altering the pipe size on the time it takes for benzene to reach the saturation concentration in water. Plot the concentration of the benzene in the water for the following three pipe sizes on the same graph: the 1-inch diameter pipe, a 3-inch diameter pipe, which we have calculated in this video, and a 6-inch diameter pipe. Assume that all of the pipes are 100 feet in length and use the same time values, i.e. the t-span, as in the example we have shown in this video. With that data plotted, please answer the following questions. How does the pipe diameter impact the time required for the benzene to reach its saturation concentration? And number 2, would changing the length of the pipe segment used change the time required to reach the saturation concentration? In the next 2 videos of the course, we will be discussing the volatilization of benzene from water to air after leaving the pipe system, the equations required to understand the volatilization model for the benzene, and the MATLAB model for the benzene volatilization itself. On the screen now are all the relevant sources that we have used to pull the data for this model, as well as establish model equations. Thank you for taking the time to watch this video, and we hope you enjoyed the module. If needed, please reference the video again to help you determine a solution for the quiz presented on the previous slide. Thank you.